Yeah.
Thank you for the kind introduction. Well, the title was mentioned already. My name is Jenny Köckritz. Also, sorry for the surname. And I'm going to present the results of a small investigation that I did in the last half year about the fatigue life of actual use case parts manufactured by selective laser melting. So the goal was to investigate not a specimen, which we find a lot in literature about additive manufacturing, but the fatigue life of realistic use case additively manufactured parts. And we selected front wing attachments out of 2139 aluminum produced by selective laser melting. Also, we wanted, sorry, was it silver? Also, we wanted to investigate the effect of an industry standard surface treatment, which you can find at producers, and also assess the player behavior under a complex load, again, in this use case part. The use case that we selected are these front wing attachments for a race car, highlighted in red in the picture here. They have a multitude of requirements. So for example, they have to be very lightweight and still carry the load of the complete of the whole front wing together with all the loads applied there. The loads involve aerodynamical loads, but also impact loads and quasi-static loads. And in addition to that, they also have to show a very good aerodynamic behavior because they have to guide the airflow downstream to the parts of the rest of the race car. I'm going to dive very shortly into the design process because this is supposed to be realistic. So first, we did an initial topology optimization of the design space. Based on that, we did an aerodynamical optimization of the outer shape of these parts. We used this outer shape as an starting point for the topology optimization of the inner structure. And the result were thin-walled hollow pieces, which have varying wall thicknesses and some inner structures for stiffness. We performed fatigue tests on these parts in 2 surface conditions. And also we did roughness evaluations and factography after damage. So the loads that are acting are, as I mentioned, 1, the aerodynamical loads, 2, some quasi-static loads, which come from regulation, not that important. And 3, I showed in the video, due to the low ground clearance of these front wings, you very frequently have impacts with the road if we have bumps. It's highlighted by the red arrow there. It's actually an impact. And so these impacts can happen either on the edge or in the center of the front wing. And we focus on the centric bump impact as a fatigue load because it is the maximum load that occurs. That's also validated by measurements. And it occurs so often that we have to consider fatigue here. To perform the fatigue experiments, the attachments that I showed you earlier were scaled at a factor of 1 to 3 to allow for more parts to be manufactured. And we tested 18 specimens in 2 surface conditions. Both surface conditions, so both types of parts underwent a T4 heat treatment before surface treatment, or no surface treatment, as is usual for this aluminum alloy. We tested as built specimen, so only support structures removed, nothing else done, and trivialized, which some of you might know more under the term vibratory cut. And both of these are shown on the lower pictures here. The fatigue tests were performed in a test rig with force that's applied at an angle and at an offset. The result is a multi-axial load case. And the highest tension stresses under a stress ratio of R0 actually can be seen here in the lower part of this front wing attachments. So based on our knowledge, we all would assume, hey, we have this polished parts, they look quite good on the picture, they will show a better fatigue life. However, our experiments showed that this didn't happen. In this diagram, you see in blue the as-built specimen and in orange the trovolized specimen. And there is no significant difference between the two. We might observe a little bit less scatter in the as-built specimen, which is also not very intuitive, and maybe a bit more inclination in the trovolized ones, but this is not a huge difference. So the question is why? So first we're going to look at the surface measurements that we conducted. The surface measurements were done in the area of highest stress at the lower edge with a confocal microscope. And the results are displayed in this diagram. Surface measurements were done for all specimens. So the first thing we can see on the left side here, the line roughness value of RA and RZ did actually show an improvement with the trovolizing. So we reduced RA and RZ. However, if we look at the values of the deepest valleys in the measurement area, we see a big scatter and not a huge difference between the two. If we look at the topography of the as-built specimen, we see kind of a bumpy surface with some baked on particles, some valleys, some peaks. And if we look at the topography of the trovolized ones, we see that a surface treatment was actually able to take off all the peaks, but wasn't able to reduce the valleys at all, which are the detrimental effect for fatigue in the end. So SV values were not impacted. And also, if we compare the SV values of the individual specimen with their fatigue life, we cannot observe any kind of effect, which we should see. And the reason for that is that the critical defects actually are not always located in the area of high stress in these parts. So let's have a look at these critical defects. At all of the specimen, we could observe crack initiation at a huge printing error defect, here in one of the as-built specimen and here in one of the trovolized specimens. And the defect depth was between 50 microns and 800 microns. And we have a thin-walled hollow piece, so this is a significant part of the wall thickness. If we look at the geometry of these defects, we see that we have huge undercuts, we have sharp notches, and maybe a few residual particles. And we can observe crack initiation at several points at these defects. And we also did some EDX measurements of these defects, and we can observe huge oxygen concentration in these. So they very likely originate from the printing, because this specific alloy, this 2139 alloy, needs very high energy densities for printing. At the same time, we have a very thin-walled piece that doesn't have a lot of support structures, so heat isn't dissipated very well. In combination with of the alloy with the geometry, that means we have a higher chance of printing errors to occur here. If we also look at the defect position, we can observe that the defects are, as I said, not always located in the area of high stress. So in the upper picture, you see the as-built specimen, crack path, and location of the crack initiating defect, and in the lower, the same for the trovolized specimen. So as I mentioned before, the highest stress occurs at the rear edge of the specimen. And if we look at the distance of these crack initiating defects from the rear edge, so kind of highlighted by the little black arrow, we can see that in the as-built specimen, the crack initiating defects were much closer to the actual stress concentration, while in the trovolized ones, the defects were further away. Okay, if they're further away, lower acting stress should have a longer life. However, if we look at the defect size, the defects which led to damage in the trovolized specimen were also a lot bigger. So in combination, we have defects which are further away, but have a higher size, And so in combination, the effect on fatigue life kind of gets cancelled out. This explains, however, the bigger scatter for the trobolized specimen, as well as the slightly more inclined SN curve for the trobolized specimen. We can kind of correlate for this specific use case that the fatigue life of the individual specimen is mostly dependent on the defect depth, which is not very surprising, and the defect location in terms of distance from the edge. The scatter along the edge, which you also saw, which you also can see here. Here. The scatter along the edge didn't play such a big role for this use case. However, the correlation is not very good. I know that, but still, this is the one that shows the best correlation here. In conclusion, we could see that in our use case, the surface treatment didn't show any effect on the fatigue life. The reason for that was that the surface treatment that was selected, this industry standard surface treatment, wasn't able to remove all the deep crevices, which where the fatigue cracks initiated. The fatigue life correlated best with defect depth and defect position. And I have to add, even though I showed all these huge defects, that the parts that we produced and that we tested performed much better than the material values of, well, actually fatigue tests that were done with this alloy by the producer who provided us with these parts. So still the parts outperformed the expectations that we had. We did observe some use case specific failure behavior. So due to the thin walled hollow structure, we didn't need a lot of support, which is actually pretty good if you look at additive manufacturing. However, this also meant that we didn't have good heat dissipation here, and printing errors were more likely. Also, this 2139 alloy is very brittle. So we could observe sudden crack growth, and also sharp defects might be more critical, well, will be much more critical here, even if they're small. Overall, if we look at additive manufacturing by powder bed fusion with laser, maybe here, we could say, well, I will say that surface treatment like trobolizing, vibratory grinding, plasma-lytic polishing, or the chemical mechanical polishing that we saw earlier might have a good effect on the parts if there's less printing errors. So if you have a well-printable alloy and you have less defects, this might work better. And if you are going to perform confocal microscopy to assess the surface quality of your part, do measure huge areas around your actual stress concentration to be sure to cover all possible defects, which can lead to fatigue failure. Okay, with this, I want to conclude my presentation, and I'm looking forward to your comments and questions.